The Math Center presents the Law of Large Numbers. In this presentation, we'll talk about using probability and then introduce the Law of Large Numbers and talk about what it means, and finally give an example. Let's start by looking at a probability example. If you take a standard coin and flip it, there are two possibilities, heads or tails. The probability of getting heads is 1/2, or 50%, since it's heads on one side and there are two possible outcomes. Now imagine we flip the coin 2 times and record the results. We don't expect to get heads exactly 50% of the time. If you flipped a coin twice and it landed on heads both times, that wouldn't be too surprising, even though 100% of the flips ended up on heads. Flipping a coin is random, so sometimes you will end up with 2 heads in a row. But now let's imagine that we flip the coin 300 times and it lands on heads every single time. That would be very surprising. Note that the results are the same in terms of percentage of heads. We got 100% to 100%. However, what is different here? What makes the second result much more shocking is that in the first experiment, we flipped the coin only twice, but in the second, we flipped it 300 times. And that's the key to the law of large numbers. The law of large numbers states that when an experiment is repeated over and over again, the relative frequency of that event, or percentage, tends to approach the actual theoretical probability. In the case of our coin, the actual theoretical probability of getting a head is 50%. Now here are some actual results from a real coin in which it was flipped 300 times. After 20 flips, you can see that we had 13 heads and 7 tails, and the probabilities are not that close to 50-50. After 120 flips, we still have more heads, but the percentage is starting to approach 50% for each. At 300 flips, we now have 154 heads and 146 tails. These are not a perfect 50%, but they're much, much closer than the 65% we had from 20 flips. If we were to repeat the process thousands or millions of times, we expect the probability to become very near the theoretical probability of 50%. Although it may never hit it perfectly, it will be very close. What does this mean, and why is it important? If we want to estimate the probability of only a few events, it can be off by a substantial amount. There can be a great deal of error. For example, if I gave you a coin and said, find me the probability of getting a head based on just a few flips, you might report back to me 100%, which is very different than the actual probability of 50%. There's a very large window of error here. However, if you repeat the process multiple times over and over, your probability calculation will be much more likely to be accurate and closer to the actual or theoretical probability. This is why when studies are done for research purposes, you try to make your sample sizes as large as possible. That increases the chances that the sample will be large enough to accurately represent the population. Let's compare 2 example studies. Which one would you consider more accurate? A study of 12 parents that looked at how many hours their children spent on the internet each day, or a study of 1,500 families that examines the number of hours each child spent online. Remember, we want to be accurate and we want our results to be as close to the actual population as possible. So we're going to employ the law of large numbers here and say that the larger the sample, the more likely the results are to be accurate. In this case, the 1,500 family study would be considered the more accurate of the 2 studies. Thank you for watching this presentation on the law of large numbers.